in this subsection, I want to introduce the Knuth-Morris-Pratt algorithm. Based on the same ideas we've seen for constructing the DFA for string matching, but trying to overcome the main weakness of the DFAs, namely their space overhead. So this is what you've just seen. DFAs are fast, but they need this transition table for all possible alphabet symbols. And it seems a bit wasteful to store all these because in the construction, we just copied a column in the table over to the next state. There's a lot of redundancy in this table. So maybe we can do away with this. And that's the third ingenious insight from Knuth-Morris and Pratt. We can do this last step during the matching instead of pre-computing it for all the symbols. If that doesn't make a lot of sense to you, it will make much more sense in a second. And the right way to think about this is, again, an automaton like this, but a slightly different type of automaton. So we use a new type of transition called the Failurelinks. So these are the things that have an X or this cross on the top, these guys here. Otherwise, this automaton is very similar to the ones we've seen before. It has the pattern on this chain to the accepting state. And now what's different is that each state only has one other link other than the matching edge. It only has one other edge, and that's the failure link. It's not exactly an automaton in the sense of formal language theory, because if you take this failure link transition, you don't consume a character from the text. So if you're sitting in state 4 and you would like to read a C, the next character in the text is a C, you're not allowed to do this because there's only an A. So you have to take this failure link, but then in state 2, you still try to read the same C. So you would take another failure link, and then you can read the C, actually. That's the main distinction. Here's a more detailed example how that works if you go through an entire text. I think I'll just show you the end result. You do the same construction or the same simulation I just sketched. Whenever you cannot follow this match edge, you have to take failure links and then try again with the same character. That's the important message here. And it can sometimes happen that you have to go through several states before you can actually process a character. If you are in state 3 and you try to read another A, you cannot read the A here, so you take the failure link. You cannot read the A here, so you take another failure link, and then you can read the A. So you go from state 3 to 1 and 0, and then eventually end up in state 1. That is the failure link automaton, and as you might already see, now we only have to store one number for each state, namely where does the failure link go? And we've lost this dependency on the size of the alphabet. So let's get you guys awake again and see if you're digested this part about failure automata already. What is the worst possible time it could take to read a single character in the failure link automaton for a pattern? How long can it take to process a single character in the text? Let's have a vote on this. I'd like to see a few more votes. That's okay. We're approaching 20. We did have up to 35 eventually. So maybe I'll give you another second. But I think people are on the right scent for this one. Okay, 25 sounds like a good number. I'll show you the results, and the correct answer is theta of m. So that's this one. The reason for that is you can basically have an automaton that looks like this. You can, if the pattern is all A's, you would indeed get this. I don't know, maybe one more. In this example, the failure links would always just go back one state. And if you have m copies of this and you're in this state and you read something that's not an A, a mismatch, you go one step back, try again. Still not an A. Okay. You try again, try again, try again. So you could take a long list going back through all the states one hop at a time. That sounds like a problem because we don't really want to spend theta m time for each character in the text. That would bring us back to essentially the complexity of the brute force method. It turns out that this is not a problem, but the reason for that needs a closer look. So let's first write down the actual algorithm for Knuth-Morris-Pratt. This is the code, and the first thing it does is compute these failure links. I'll show you on the next slide how that works. Then it iterates with I through all the guesses. That's this one, but it's not a simple for loop as it was in the brute force method. Instead, it's a while loop, and I can jump in larger increments. There are two cases. Essentially, we can either find a match. If the next character matches, then we take the match transition in the automaton. So we go from state Q to state Q plus 1. Q is the current state in the automaton. I didn't say that even though it's written here. You start in the start state 0. If you find a match, you go to the next state. And here, I is actually the position in the text. That's maybe I should have used I and J separately. So here's I is not exactly the guess. It's not the starting position of a potential match. It's the current position in the text that we read. If we end up in state M, that's the accepting state, then we can return the occurrence we found. And because I is the current position in the text, we have to go back by the length of the pattern. So this, I mean, this is equals, or this could also be written as I minus M, maybe more intuitive. If we don't have a match, so the next character is different from what we want to see, we have to do something else. We have to follow a failure link. There's no failure links for the start state. We just stay where we are. But if we're not in the start state, then we compute the failure link. So the target of the failure link is stored in this array fail. And then we just move our state there. If we are in the initial state, then we advance and go to the next character. Then there was just no way to find that character. This maybe doesn't occur at all in the pattern string. That's fine. Then we just stayed in the initial state, which says we haven't seen any part of the pattern. That's how this code works. And let's see how we can analyze it. Maybe turn myself off entirely for this part. How long does it take to execute the entire code going through this while loop with the entire text? One important observation is the failure links always point backwards, right? We never have, they always point in that direction. That's one observation. And now in each iteration of this while loop, we do one of two things for sure. We either advance in the text by one position, that happens here or here, or we shift our pattern forward So the guess I minus j, where we currently guess that the pattern starts, moves by one step forward. Okay. This is a little more subtle, but whenever we update q, this is essentially what happens. By going to a smaller state, we implicitly shift the pattern forward in the text by at least one position because of that. Now, each of these cases can only happen at most n times because there's only n positions in the text, so we can only advance the text n times. And this also advances in the text, but with the pattern. And the pattern can only advance in the text, can also only advance in the text n times. So the entire loop can only be executed at most 2n times by simply observing that each iteration in the loop makes progress, either by moving to the next character in the text or by shifting the pattern along the text forward by at least one position. So both the green and the blue can either only happen n times, and we do one thing of these at least. So the total loop iteration, the total number of iterations of the while loop can be at most 2n. And we do exactly one simple comparison in each iteration, so that's why we have at most 2n iterations and at most 2n simple comparisons. That's the analysis of Knuth-Morris-Pratt, but we excluded computing the failure links. And that is a second important part of the code. So let's look how that works. Remember that the failure links point to this error state x in the construction from the DFA. We will use the very same idea that we've seen for constructing the DFA. But instead now of copying over the columns of this transition table, we just store the state x that we are, and that's the only change we need really. So we initialize x to the start state, and the start state doesn't really have a failure link, so this will never be used. And then we do something similar. We iterate through the pattern, and we set the current state's failure link to whatever x is at the time. And then we update x. So there's two options. Either we can read the next, if we can read the next character and it's the same as in the pattern, so we can extend the match, then we move with x along the match edge. And that means we just update x to x plus 1. If we don't have a match yet, then we have to follow failure links. But luckily, these are the failure links that we already computed because they're further to the left. So if we've already reached the start state, then we do nothing. And a quirky way to say this is we set x to -1 and then increment it again. Maybe a different flow in the code would have made this more intuitive. If we're not in the state, then we just follow one failure link and then try again. So it's, in a sense, we're using the part of the automaton that we've already constructed to simulate what would be the next step for x. And we always store what x was in each of the positions. And again, we want to analyze how long this takes. This loop takes m iterations. That's easy. But we have this inner while loop that could take our running time beyond m. But indeed it doesn't, because this inner while loop, it always makes m smaller, namely here. Remember again that fail is always smaller than its argument. So that's this part. And we only increment x once per iteration of the outer while loop. So x only ever gets bigger here. So there's no way this inner while loop can be executed more often than the outer while loop. we can basically charge each iteration of this inner while loop to one iteration of the outer for loop. And we only have m iterations for the outer loop. So that means we can in total only have m iterations of the outer loop and m iterations of the inner loop at most. That's another 2m symbol comparisons for computing the failure links. So that's 2m. Previously was 2n for the text. In total, it's 2 times n plus m. That's what's written here. That's the time. The character comparisons are 2 times n plus m. And this is optimal in the worst case. There's no way you can do better. The Knuth-Morris-Pratt algorithm basically gets the time that you need to just read the two pattern, the two text, the pattern and the text. So that is the best possible that we can hope for. And the space is essentially as big as the pattern, but there's no dependency on the alphabet. That's, again, almost as good as it can get. But we'll see some further tricks later down in this unit. So the total time is asymptotically optimal in the worst case, and that's for any alphabet size. That's really important. And the space overhead is much better than for the DFA. That's the Knuth-Morris-Pratt algorithm. Any questions about this? Then I have one question for you. Just reflecting a bit and stressing that part again. What are the advantages of KMP? You should be able to answer with multiple answers, so check all that apply. And yeah, I'll leave you with that for a minute. Okay, we have some votes, but maybe we can get a few more. I'd like to see at least the 25 that we've had before. "24, one more." The fingers over the mouse. One more, guys. I see things moving, but people just change their votes. We have 25. So here are your answers. And the main points are, let me show this on the other part. KMP is faster in terms of the pre-processing because we don't have to factor sigma. It uses less space. That's something I've stressed a lot, so almost all of you ticked this one. And it makes also the entire running time independent of sigma, which is an important fact if you use, for some reason, a very large alphabet like you have. You allow the entire Unicode alphabet. The Knuth-Morris-Pratt algorithm is very useful for string matching, and it was the first worst case optimal algorithm for this problem. But it turns out that the insights that led to it are much more general than just this algorithm. And indeed, there's this failure function that we used, fail of q, which was the failure link target. In the literature, there's a thing called the prefix function, often denoted by capital F. That's why I didn't use F for our failure function, which is very slightly different, but it's almost the same as you can see here. essentially just a shift in the argument. And this failure function, this prefix function, sorry, has found uses in many other problems in stringology. Whenever you try to answer problems that answer questions about strings that have to do with self-similarity and overlaps and partial matches, often there's a way to formulate it in terms of this prefix function. So this has become useful and important way beyond the classic string matching problem. So I want to briefly discuss this here as well, just so that you're aware of the notation and can relate to this. So again, let me indicate this here to make the connection. This is how I defined the fail function. The prefix function is defined as the length of the longest prefix of this pattern. That is a suffix of, well, the substring, it's the same prefix of the pattern, but with the first character omitted. Okay. And that's also, if you translate this to our fail function, you get the following property about fail of j. And this is really, really useful, and you should definitely memorize this. And let me draw the picture that belongs to this. Here we have our prefix up to excluding this, the jth character. And now fail j is the length of the longest prefix. So here's the same thing again. Same thing again, but a bit shifted. Now again, yeah, I've drawn this many times. I want that these two parts are equal. So there's a self-similarity in this string. There's a part at the end, a suffix that is also a prefix. Okay. So fail j is the length of the longest prefix of this thing, this prefix, the one that ends here. So this blue part is then only something smaller, j prime. And this blue part is the longest prefix. That is also a suffix of, that occurs again here, a suffix of this, and at least one pattern is omitted. So this one means that here is at least one character of a gap. We shift this right by at least one position. And then finally, fail j is just the length of this thing. And that is nothing but this j prime. So it's this length. It's the length of the overlap. Okay. This is all I want to say about the prefix function. We will have a closer look at KMP and the prefix function, or the failure link function, in the tutorials to practice that a little bit. I think memorizing this picture and this definition is helpful. If you ever see the f and the prefix function used in some book or paper, then be aware of this offset. It's at the end down to the question: do strings start with a 0 or with a 0th character or with the first character? To be consistent, I chose that strings start with a 0. So that has certain implications and makes some definitions nicer. Here it means that there's a slight difference to how things are done in many books. Okay, with that, let's close the chapter on KMP. We'll continue tomorrow a little bit more on string matching. We've seen that KMP is an optimal algorithm, but it turns out you can beat it. You can improve upon this optimal algorithm in an interesting way. And well, I'll tell you more about this then tomorrow. And we'll also conclude this unit then.